Hello guys, welcome back to our channel. As I was saying in the previous videos, now I'd like to show you guys how to calculate um, reinforced concrete beams whenever we have compressive reinforcement. These sections we tend to call them doubly reinforced sections because not only we're going to have the tension reinforcement, but we are also going to have the compressive reinforcements. The compressive reinforcement will be in the phase where we are going to have compression, okay, during flexure. So, for example, if we have a regular bending flexure, as we said before, the top phase here in this situation is the compression, and this one is in tension, okay? So here we would place AS prime, and here is going to be AS, okay? You should be careful because whenever we have a different flexure like this section here now the top will be tension, whereas this one will be under compression, okay? So don't take always like the bottom reinforcement is going to be the tension one, okay? This is not how usually we play like this, okay? So you have to be careful. So Yuri, what are the main differences whenever we're designing doubly reinforced sections? Here, as you can see from our strain relationship that we talked through last class, we have a linear behavior here, of course, and we have at the top the ultimate compressive strain of concrete. At the bottom, we have the tension strain, which should be bigger than the yielding strain, as we talked about for ductility purposes. And here, on the compression part here, there is also the strain of the compressive reinforcements, okay? The distance from the top layer to the center of mass of the compressive reinforcement, we're going to call it d prime, okay? And just d is going to be the distance from the most outer layer of compressive concrete to the center of mass of the tension steel. Okay, we use these terms because sometimes you might have more reinforcements distributed through the depth of the beam. So these D and D prime, they should be checked. Okay, we're not going to talk about this in this class, but maybe in the future. Okay. And now let's talk about forces, okay? Forces of the section. This is very important here. As we saw previously, for the tension reinforcement, the forces will be the product of the area of steel reinforcement times its yielding strength, okay? Assuming that this reinforcement will yield, okay? And above the neutral line, we have our regular compressive stress block, okay? Defined by the alpha 1 times F prime C. And also we have another one, which is the last component, which is going to be the compressive reinforcement. This force, we call it CS, okay? CS is going to be defined by this equation here. So it's going to be the area of steel reinforcement in the compression phase times this part, which is going to be the stress in the compressive reinforcement, okay, in the compression phase, minus that part that was supposed to be carried by the concrete. Okay, so this is what physically what it does is the compressive reinforcement takes part of the tension of this stress, sorry, that is upholding that phase. Okay, so it's defined by this. And the compressive force of concrete, it's what we saw in the previous lesson. So it's going to be CC, which is the whitening stress block multiplied by the volume of the stress block. Okay. And so what we have for the section then is three forces instead of only one acting on here. Okay, so that's the main differences. Instead of checking equilibrium for only two forces, we're going to check equilibrium for three forces. So this is very simple. Whenever we're talking about T sections, the same thing is going to happen. But in the sixth section, this T section, we're also going to consider the force of the flange. Okay. Yeah. One last thing here is the lever arm. So the lever arm should be between the center of mass of these two forces towards the T. Okay. These usually sometimes can get confusing. So instead of using either uh, these forces, we're going to calculate the resisting moment capacity using their distances, because we know from the C to T and from the CS to T. Okay, so we're going to use this both. And the equation is like this. The equation was supposed to be here. Where is it? I did not put in here. So, okay. The equation, well, we can deduce the equation. The resisting moment now, it's going to be the force CS times its distance towards the force T right here. Okay, so CS is here. So CS is this distance here to here. So it's going to be D minus D prime plus the force of concrete under compression, which is going to be this distance minus D. So D minus A over 2. Okay, so that's going to be the equation. All right. Lastly, one thing that we should check is where can it be tricky is that we don't know prior the stress of the compressive reinforcement. Yeah, we have to determine that. So this can be very tricky. So we need to do what we call an interactive process in which we're going to calculate the stress on the compressive reinforcement, and then we're going to check the through it using the string. All right. So the idea here is pretty much we're going to try a C, specific C. So we don't know exactly the where the position of the neutral line is. So we try one, and then we check to see if we have equilibrium. Okay, so that's the main idea behind it. Here are some notes that I made for you guys. So the equilibrium is reached whenever the T force, so the force in the tension reinforcement, is equal to the forces in the compression phase of the concrete. All right, with the compressive of concrete and compressive force of the compressive steel. All right. The selection of C usually is between D over 4 or D over 3, okay? But this is not always true, okay? You can have a very low depth of neutral X. So this can be complicated because, in fact, whenever you add compressive steel, you reduce C, okay? You will reduce the position of the neutral line, okay? But as an addition, you can increase a lot ductility, and you will have a slightly increase in moment capacity, okay? So Yuri, why do we add compression reinforcement? Well, compression reinforcement sometimes is very important because we want to have ductility. So ductility is the main reason. But also, whenever we're talking about creep effects, and creep effects is the very slow deformation that will rise throughout the lifespan of concrete. So we can reduce that as much as 2 times or even 3 times. Okay, there's the book of McGregor in which he indicates this. So this is a chart where it represents the creep effects related to deflection. Okay, so if you have pretty much the same amount of compression reinforcement with tension reinforcement, you will gain a lot of service deflection, okay, throughout life. So this is really good. So this is important. And here is the increase on ductility. Okay, so this is the relation between bending moment and curvature. Okay, so if you increase the compression reinforcement, you tend to increase a lot the curvature response. So this increases ductility. So this is really good. Okay. I also put here the process from the book of McGregor. What are we going to do throughout the steps? So first of all, we are going to assume that the deformation on the tension reinforcement is going to be yielding. Okay, so we assume that there is yielding first, and then we select C, and then check deformation. After checking the deformation, we are going to calculate the stress in the compression reinforcement, then the section forces, and then after we check the section forces, we see if we reached equilibrium. If we reach the equilibrium, we calculate officially the strain and the tension reinforcement, and then we calculate the bending moment. And then what happens if we do not reach equilibrium? So if the compression forces are bigger than the tension forces, we just reduce the depth of the neutral line. If it's the opposite, if the tension reinforcement gives more strength than the compressive components, then we increase the C. So it might be a little bit tricky, but I'm going to do an exercise right now with you guys so you can actually see this is actually very simple. Okay, it's the same exercise from previously, so from previous exercise that we done, but we are adding compression reinforcement here. Okay, so let's check this.